China's most important chip move this year has nothing to do with transistors. A facility in Shanghai is stitching chips together in a way that, on paper, shouldn't let China compete at the top of artificial intelligence hardware. And yet, the performance numbers coming out of assembled chiplet packages are closing in on what only the world's most advanced fab was supposed to deliver. Before you flag this as hype, this is not about China suddenly equaling TSMC. The lead TSMC holds is real and large, but the location of the competition has shifted, and that shift is what actually matters here. The entire architecture of Western chip export controls rests on one assumption: that leading artificial intelligence performance requires leading transistor nodes, and that China can't print those. Advanced packaging challenges that assumption at its foundation. By the time we're through, you'll understand how packaging works, why it opens a second lane to artificial intelligence performance, what China has actually built at Shanghai Lingang, what TSMC's chip-on-wafer-on-substrate advantage really consists of, and whether raising the floor is a genuine strategic threat or a consolation prize dressed up as a strategy. Here's the first reframe. This isn't really a story about one factory. It's about whether the choke point that was supposed to decide the artificial intelligence chip war is actually the only choke point that matters. 3 questions are going to pull through everything that follows. First, extreme ultraviolet lithography is the tool everyone said you'd need. So, how is a facility without extreme ultraviolet access producing competitive high-performance packages? Second, packaging has historically been commoditized, low-margin work. So why does it suddenly matter enough to build a national strategic base around it? Third, the Lingang base is real, but how big is it really? Those answers come in order. To understand why any of this matters, you first need to understand what advanced packaging actually is, because it is not the packaging of 20 years ago. Legacy back-end work was simple encapsulation. Put the chip in a case, wire bond it to a board, ship it. The chip did all the work. The package was just a container. What TSMC's chip-on-wafer-on-substrate platform does is categorically different. It stitches multiple chiplets, separate silicon dies, each manufactured independently, onto a dense routing layer called an interposer. Data moves between those chiplets through the interposer at speeds approaching what you'd get from connections made directly on a single die. That's the mechanism that makes assembling performance possible, rather than merely theoretically appealing. High bandwidth memory fits into this picture at the point where it matters most. High bandwidth memory stacks multiple dynamic, random access memory dies vertically and then connects that stack to the compute die through the interposer. The memory bandwidth that artificial intelligence training depends on, the speed at which data moves between memory and the processor doing the math, flows through that joint. Block that joint, constrain that interposer, and you constrain the whole system. Think of it this way. Legacy packaging is like running one large pipe from a single reservoir to a city. Advanced packaging is building a distribution network, multiple smaller reservoirs, high-speed connectors between them, pressure matched at every junction. The city gets more water delivered faster without needing a bigger single source. The interposer is the junction box everything routes through. That analogy does the job, and then we can leave it behind, because the mechanism is straightforward once you see it. You might ask, why not just make the chip bigger instead of assembling multiple smaller ones? You can, up to a point. But yield drops exponentially as die size grows. A single large die has more surface area and more chances for a defect to ruin the entire thing. Chiplets let you manufacture smaller dies with better yield, and then select the best ones to assemble together. That's the economic argument as much as the performance argument. Advanced packaging is not a workaround for people who can't build big chips. It is often the smarter engineering choice even when you could. That's the answer to why back-end is no longer simple commodity work. When the interconnect density reaches this level, the package is part of the performance architecture. Now, why was the transistor-node race assumed to be the decisive choke point? And why were export controls built around it? The October 2022 Bureau of Industry and Security rules, and the waves that followed, targeted advanced chips above certain compute thresholds, and the equipment needed to manufacture at sub-14 nanometer class nodes. Extreme ultraviolet lithography is the gating technology that makes sub-7 nanometer class production achievable at commercial scale. Without it, you are doing what SMIC has done, using deep ultraviolet multi-patterning to approximate smaller nodes, which is expensive, slower, and capped. What teardowns and analyst inference suggest, though SMIC has not confirmed any node name publicly, is that SMIC reached something in the 7 nanometer class through this method. 5 nanometers and below remain out of reach without extreme ultraviolet. TSMC's chip-on-wafer-on-substrate sits behind that wall. It is integrated with TSMC's leading node wafer production in Taiwan, which China cannot access. The export control logic was linear. Frontier artificial intelligence performance requires advanced nodes. Advanced nodes require extreme ultraviolet. Extreme ultraviolet is blocked. The chain was supposed to be unbreakable. The export control architecture is like a bridge toll designed to stop heavy trucks. The assumption is that if you can't pay the toll, can't access extreme ultraviolet, you can't move the freight. Advanced packaging is the question of whether there's a way to move that freight in smaller loads, each one coming in under the limit, and then reassembling it on the other side. And if you're wondering why China doesn't just build or buy extreme ultraviolet, ASML's machine draws on over 5,000 suppliers and took roughly 30 years to develop. SMEE, China's domestic lithography company, is working on advanced deep ultraviolet tools, not extreme ultraviolet, and per industry reporting, remains well behind where ASML was a decade ago. That door is not open on any near-term timeline, which is exactly why packaging becomes the strategic alternative. The Shanghai Lingang advanced packaging base targets precisely the assembly steps that sit above the transistor level. Its announced focus is high-bandwidth memory, back-end integration, and chiplet packaging, the specific capabilities needed to assemble artificial intelligence accelerators from mature node components. If you can source mature node chiplets domestically or from permitted suppliers, and if you can assemble them with chip-on-wafer-on-substrate class precision, you can close a portion of the performance gap without printing a single advanced transistor yourself. The strategy is to build at the layer above the choke point. China's mature node capacity, fabs running at 28 nanometer and above, is substantial. The Lingang approach is to take what those fabs can make and assemble it into something the node gap alone wouldn't have permitted. AMD demonstrated that this logic works commercially. Instead of one giant chip that's hard to manufacture without defects, you tile smaller chiplets that each yield well, then stitch them together. AMD's Zen architecture showed the performance is close to monolithic, and the manufacturing economics are better. China is applying the same logic strategically. Use the chips you can make, assemble them into the system you couldn't otherwise build. That's how you route around extreme ultraviolet without pretending the requirement doesn't exist. The tool everyone said you'd need, extreme ultraviolet, is avoided by operating above the transistor layer entirely. If TSMC moved the ceiling at the same time others were learning to assemble, why didn't someone use chiplet strategy to avoid TSMC's advantage years ago? Because the pressure wasn't there. Advanced packaging as an alternative path only becomes strategically compelling when the node road closes. When you can still buy access to leading-edge wafers, you do. When that access is cut off, you find the lane that doesn't require it. But here is where the floor versus ceiling framing earns its keep. Raising a floor and reaching a ceiling are not the same thing. The honest picture separates what Lingang is from what it has been verified to deliver. Lingang is a real facility with real announced capability in high bandwidth memory, back-end, and chiplet packaging. Government announced and reported. Volume and yield are not publicly confirmed. TSMC's chip-on-wafer-on-substrate lines are, by all independent reporting, years ahead on volume and yield. That framing, years ahead, reflects analyst consensus, not a specific figure anyone has published. But the direction of that consensus is not seriously contested. More structurally, the interposer and chip-on-wafer-on-substrate is itself fabricated on advanced nodes. TSMC makes the routing layer between chiplets on the same leading-edge process that China cannot access. That means TSMC holds a structural advantage even within the packaging domain, not just in transistor fabrication, but in the substrate that does the stitching. China cannot replicate that interposer layer today. Then there's the yield challenge in chiplet assembly itself. Every additional die you add to a package is another chance for a defect to compromise the whole thing. Assembling many mature node dies into one high-performance package is a genuine engineering and economics problem. Mature dies yield better individually, but the assembly process adds its own failure modes. Building a known good die supply chain, testing every chiplet before bonding so you're not wasting expensive assembly steps on defective silicon, is non-trivial at scale. High bandwidth memory supply to China is also restricted under export controls, and whether China's domestic DRAM producer has reached high bandwidth memory class, stacking at volume is not confirmed in public reporting. So, is China's packaging story real or government announcement theater? It is real as a capability investment and a strategic direction. It is not yet verified as a volume competitor to TSMC's chip-on-wafer-on-substrate lines. The floor is being raised. How fast and how high is the empirical question that public reporting has not yet answered? Narrowing on concept, not yet on quantity. Those are very different things. Zoom out, and the pattern changes what you think the controls were actually protecting. The export control architecture assumes a linear dependency chain. Advanced packaging introduces a fork. It doesn't eliminate the dependency on leading node wafers for everything, but it means the performance achievable without those nodes is higher than the architecture assumed when it was written. The strategic consequence is not export controls failed. It is that the ceiling they enforce is lower, relative to what can now be assembled below it, than it was when the controls were designed. There is a documented concern in policy discussions, not a confirmed regulatory hole, but an analyst and policy commentary concern, that back-end equipment controls have lagged front-end controls in specificity. The October 2022 and subsequent rules targeted leading-edge chip manufacturing with precision. Advanced packaging equipment coverage is a policy discussion still in progress. That distinction matters. It means the export control architecture may need to evolve to address the lane that's now being used most actively. TSMC's interposer advantage means the ceiling doesn't just stay out of reach. It stays out of reach for a structural reason that isn't easily engineered around. But interposer design can, over time, be separated from leading-edge node fabrication. It's an engineering problem with more than one potential solution, not solved, not trivial, but also not permanently sealed in the way that extreme ultraviolet supply chains are sealed. Here is my honest read. The people who say China's packaging push is a substitute for not having extreme ultraviolet are wrong. It's not a substitute. It's a workaround that closes part of the gap, while the other part stays open. The interposer layer, the volume, the yield maturity, those gaps are real. And the people who say it doesn't matter, because TSMC is still years ahead on chip-on-wafer-on-substrate volume, are technically right, but strategically incomplete. Volume leads erode faster than node leads. Back-end capacity is buildable on a shorter timeline than extreme ultraviolet supply chains. That's a reasoned inference from how capacity has been built, historically, not a documented fact, and I want to be clear about that. But the direction of the inference is sound. The gap that matters most in 3 years may not be the one that's largest today. China chose the lane where the contest is closest and is investing specifically there. That is not a win. It is a genuine strategic position that deserves to be watched, not dismissed. The export control bet is that the ceiling moves faster than the floor rises. Advanced packaging makes that bet less certain than it was when the controls were written. Here is what I genuinely want your read on. As China's packaging floor keeps rising, does the transistor-node gap that export controls were built to enforce stay decisive? Or does a high enough floor eventually make the ceiling less relevant? I want your honest answer in the comments, and I mean that. The people watching this tend to have thought about this longer than most, and I want to know which side of that question you come down on, and why. Subscribe if you want to follow the back-end capacity data and yield disclosures that will answer this empirically over the next 12 months. That's the evidence that actually matters, and this channel will cover it as it comes in. A facility in Shanghai, stitching chips together without a single extreme ultraviolet machine. The floor keeps going up.